to everyone.
Hi, I am Engineer Doctor of Pilones of Gatmaitan Institute of Technology. My students in Strength of Materials are going to discuss about torsion. I hope you're going to enjoy and learn about this topic because it's going to demonstrate the activities and applications about our daily life. Thank you very much.
In engineering industry, torque is usually visualized in machine designs with parallel planes. One simple example for this is shaft. Torque refers to the rotation of an object upon application of force. The relationship of the applied torque and the angle of twist was developed experimentally and analytically by engineer C.A. Guzman and engineer A. Pilones, respectively. Engineer Pilones derived the mentioned relationship having assumptions of a plane section before twisting remains plane after twisting and that the region line on the cross section remains plane after twisting. With this, the derived equations is applicable for solid or shallow circular shafts only.
Figure shown as the round shaft is twisted, applying torque at the end. Each longitudinal grid line is twisted into a helix that intersects the circular cross sections at the equal angles. Still, the radius and the length remain unchanged. Unlike a shaft, the plane cross section of the square shaft will not remain upon the application of torque.
For us to fully understand the relationship between the applied torque and the angle of twist, we first consider the figure shown. The figure is a circular shaft having fixed length L and radius R and is rotated at the ends. The torsional shear stress tau at a distance ρ from the center of the shaft is given by shear stress is equal to torque times ρ over J, where J is the polar moment of inertia of the section. For a solid cylindrical shaft, J is equal to pi over 32 times d raised to 4. For hollow cylindrical shaft, J is equal to pi over 32 times the quantity outer diameter raised to 4 minus inner diameter raised to 4. In addition with this, we can also consider Hooke's law, wherein shear stress is equal to G times shear strain. In shear strain and angle of twist relationship is shear strain is equal to ρ times d theta over dx. Equating all the equations, the resulting working equation is G times d theta over dx is equal to T over J. Integrating with respect to the longitudinal coordinate over the length of the segment, the angle of twist can be expressed as theta is equal to T times L over J times G.
Here, we have a sample of how the angle of twist formula works. We have here a circular shaft made of alloy steel. Its length is 1000 millimeters, so its length could also be expressed as 1 meter, and it has a diameter of 100 millimeter. Its polar moment of inertia could be determined from the formula pi over 32 times the diameter to the fourth because it is a solid cylindrical shaft. Using the Excel to compute for the angle of twist and plugging in the values, we can see that its angle of twist is 0.01289 in radians. If we want to find it in degrees, we just need to multiply it to 180, then divide it by 3.14. So its angle of twist is 0.74 degrees.
were given with a problem involving a circular shaft, and we want to know what would be the angular twist subjected to the conditions stated.
We can use this application called SolidWorks to simulate such. Here it goes. Click on New, click Part, then click OK. We want our length to be in whole numbers rather than 2 decimal places, so there. Right click on right plane, then click Sketch. Then construct a circle. Then click on Smart Dimensions since we want a circle with 100 mm diameter or 0.1 meters. Click on Features and extrude base for us to have a length of 1000 millimeters or 1 meter. Then click Check and wait for it, then save it with the file name of circular shaft.
Click on SolidWorks add-in, then SolidWorks simulation. Probably it would take 30 seconds or less. Then click on simulation. And then click on Study Advisor, New Study, and let's name it as Torsion, and then after naming, click Check. Right click on the name Circular Shaft and apply Edit Material. Since we are dealing with alloy steel circular shaft, then we apply alloy steel. From the picture, elastic modulus, ratio and shear modulus are given. And click apply and close. Let's apply external loads such as torque. We apply torque on this particular face, and we want the axis to be in the body of the shaft. And then we are dealing with 10,000 Newton per meter of torque. Based on the problem, the shaft is fixed at one end. So we fixtures, then fixed geometry for translational or rotational degrees of freedom to be at 0. And after that, we want to see the isometric view. Then there you go. There's the isometric view. And click again on fixtures, roller slider, so that the body cannot move in the direction normal to its plate. So roller slider being applied on the body, and then hide all fixtures and external loads, and we are ready to go. And go, run the study. Wait for it, wait for it. There you go. Since we are not concerned with URS or mean resultant displacement, we change it to UY, mean displacement. Then click on chart options, click show and mean max annotation, and we get a minimum of 6.308 times 10 raised to negative 1 change in Y, and max of 6.108 times 10 raised to negative 1 change in Y. Computing and comparing the values we get from our simulation, we add the two values obtained and divide it with 100. We get 0.012488. As you can see, it has a slight difference from what we computed, but nonetheless, it is still acceptable.